The creation of this video is sanctioned by the Organization for Human Advancement. If there are any problems with the information provided, contact the Ministry of Information Dispersal to file a complaint. Thank you and enjoy.
Welcome back, friends, to the saga that is Samsara III. Our voyage through geologic time is designed to inform you about the planet that has become humanity's exotic black and blue marble. Some of you may be watching this on your way to the planet itself. Some of you may be watching this for your own enjoyment. I respect both decisions. I am Professor Dragonborn Homo sapiens, foremost expert on Samsarian paleontology. Without further ado, grab your notebooks and pencils, turn your textbooks to page 108, and listen up. We've reached the middle third of the Archethermic period, which, if you don't remember, considering it's been a while since the video on the early Archethermic, is a period of Samsarian deep time characterized by extreme warmth and wetness. High sea levels have led to a vast amount of shallow waters that are perfect for sustaining life. The world map currently looks like this, if you're interested in that sort of thing. Following the end Protogene extinction event that capped off the previous age, the first 30 or so million years of this period led to a radiation of many clades that have adapted well to the current global environment. Some notable examples include the Ammoderms, Uropods, and Pelterpetinids, but there are a handful of other clades known from the fossil record. Admittedly, our knowledge of Samsarian prehistory this far back is quite limited. Fossils predating the Fimbulveteric period that follows the Archethermic are incredibly uncommon and most often fragmentary, simply due to the geological conditions of the Fimbulveteric. More about that at a future time. Our paleontological knowledge of the Protogene and Archethermic are the result of hundreds of OHA researchers working incredibly hard to piece together the story of our new secondary home. Perhaps surprisingly, we have found relatively extensive impressions in certain shale deposits depicting a plethora of soft-bodied organisms, including many species of stomazoan, which as far as we know remained relatively unchanged for the first 45 million years of the Archethermic. We naturally have no exact answer as to why, as there are a multitude of possibilities. Perhaps they were hit unusually hard by the mass extinction, perhaps it was difficult to adapt to a much warmer climate, perhaps there was an unusual lack of evolutionary pressure to adapt. It's impossible to say. That being said, we know that they picked up the metaphorical pace around 500 million years ago with the first known evolution of the clade Cladostoma, a group of odd-looking trisulcostomes that are typically quite tall with an average height of 4 meters, but with some species estimated to be capable of reaching 10 meters or taller. They are named for their spindly little mouthparts, which, as with other trisulcostomes, are used to filter feed, catching planktonic organisms that drift past using a web of tiny fibers that extend from the arms and main body of the mouthpart. It is thought that the mid-Archethermic underwent something of a trophic upheaval with a large influx of microorganisms into the environment. There are several examples of filter feeders growing to massive proportions around this time, which help support the idea that ecosystems were more productive than they previously were. It's theorized that these creatures grew continuously as they aged, but their actual lifespan is unknown, as the whole group vanished alongside most species at the end of the Archethermic period. Cladostoma was not, however, the only new stomazoan clade to appear around this time. The earliest known fossils of species in the clade Chistoforma were found in the same rock formations as the cladostomes. Chistoforma is actually still alive today and remains relatively unchanged from their Archethermic counterparts. It is assumed that they are descended from antistomes due to their physiology, which is, like members of the clade Antistoma, almost a complete reversal of the trisulcostome body plan. Moving in ways similar to earth jellyfish, or in some cases octopods, Chistoforms swim using undulations of their many tentacles, which, as with other trisulcostomes, are highly derived mouthparts. The so-called bladder, for which the group gets its name, is, in actuality, the main body of the organism. which is at this point so specialized that the basal condition for Cystiforma is an inability to retract their mouthparts into their body. They often have wildly reduced cardiovascular and nervous systems in order to make room for their extended muscular and digestive systems. Most in the modern day are filter feeders, rarely exceeding a few centimeters in arm span, or tongue span, I guess. In the Archethermic, however, there are species known to reach up to 30 centimeters in tongue span, such as Archaeodactyloglossys cathalensis, depicted here. Extant species are exclusively filter feeders, but it is not impossible for these larger species back then to have dabbled in more active methods of predation. We have records of many hundreds of cystiform species living throughout Samsarian prehistory and into today, and high populations typically coincide with times of plenty. Therefore, the fact that a majority of soft-bodied Archethermic fossils yet found have been cystiforms lends credence to the idea that planktonic life was thriving in the mid and late Archethermic period. A third offshoot of the Trisulcostomes appeared relatively long after the evolution of the previously mentioned groups. Lithochiridae is a fairly unknown and undocumented clade that is theorized to have planted themselves in rock to catch passing prey, perhaps including Cystiforma. I am sorry to say that we simply do not have a lot of information. There is only one known genus, Lithochirus, for which the clade gets its name, with two species, L. vulgaris and L. megalos, which are only differentiated based on size. They might even be the same species, for all we know. We have one specimen of each, which came from the same rock layer found a mere 14 meters apart. Naturally, this does not mean they were that close at the time of fossilization, but it supports that these organisms lived in quite close proximity to one another. Paleontology is a messy process. It is incredibly uncommon for us to fully understand a species that was alive an incomprehensibly large amount of time before we do. Lithochirus was one of the first Archethermic genera ever discovered. We had knowledge of and an accepted scientific name for Lithochirus vulgaris several months before we had knowledge of a native Sophont life on Samsara III, even. It would be a shame to have any documentation of Samsarian paleontology lacking mention of this enigmatic and profoundly important genus. Now, I imagine by this point you are all quite bored. I have spent the last while talking about organisms that are likely not all that interesting to the average person. This will be my one reminder today to pay attention. There will be a test afterwards. Arthroderms, which have been ever present for the last 60 million years at this point, benefited greatly from the end protogene extinction, which left most ecological niches barren, allowing for an adaptive radiation at the beginning of the Archethermic. Arthroderms got significantly bigger than they ever had before, adopting niches that were previously filled by flagellognaths. As most of you know, most of the flagellognaths died. Some Arthroderms largely kept the ancestral body plan, such as the clade Ammodermi, which are thought to have been seafloor ambush predators. However, perhaps the wildest turn of events was the evolution of the Peltoderms, which were Arthroderms that adapted to swim. They are considered convergent with Earth's Placoderms, with Peltoderms essentially being 8-eyed, boneless, fully armored fish. They radiated immediately. The Pelterpetonids and Magnerpetonids were widely successful. This success continues into the mid-Archethermic. Albodermi is perhaps unexpected. Thought descended from either the Ammoderms or more basal Arthroderms, the Alboderms seem to have lacked a full exoskeleton, a previously unheard of discovery. Emphasis on previously, you'll see what I mean later. Albodermi is thought to have traded in, so to speak, defense for offense. The reduction of armor allows for an increase in maneuverability, which coincided with sharpening of the mandibles. These creatures would have been impressive predators, if only we knew what they predated. We don't. Simulations of their mandibles using data from extant Arthroderms supports the idea that they lacked the strength to pierce the thick hide of contemporary animals. Even without that, all known Alboderm species are quite small, exclusively under a meter and frequently under 40 centimeters from head to tail. We do not have evidence of prey species of a complementary size and structure. An absence of evidence obviously does not correspond with the evidence of absence. And there was definitely an open niche for the Sklade's ancestors to fill, which they did. We do not yet, however, know what that niche was. Perhaps a new discovery in the future will shed light on these organisms, or perhaps we will be left guessing forever. Tell me your theory in the comments below, I'd love to hear it. Albodermy was not the only Arthroderm clade to evolve during this time period, however. In fact, the clade Lithodermy seems to have taken an opposite evolutionary trajectory, doubling down, so to speak, on their ancestral exoskeleton. Lithoderm fossils are often uncharacteristically well preserved due to this exact dermal fortitude. Lithoderms are also somewhat strange for their time for holding their legs directly underneath their body, which, in addition to the buoyant forces imparted by water, would allow for more weight to be put on them. This quite possibly coincided with the growth and thickening of the exoskeleton, which allowed for lithoderms to achieve a level of abundance that had yet to be seen. And the clade would last for a staggering 375 million years, only going extinct at the beginning of the Homophorus period, around 120 million years ago. The lifespan of lithodermy exceeded that of even the trilobites by around 100 million years. The thing is, we do not know what sparked this supposed evolutionary arms race that led to these armored bugs, or how they managed to last for a comparable amount of time to Earth tetrapods, despite almost never reaching particularly large sizes. There is one notable exception, being the absolute behemoth that is Paleontology ericksoni, Erickson's frost giant of the swamp. A massive 800-kilogram lithoderm found in the late Gaiferous period. It is believed to have inhabited the plentiful boreal wetlands of the North Pole, where it grazed on aquatic vegetation. It is also believed to have been constrained to the many shallow waterways in the region, as it is thought to have been too heavy for its legs to fully support itself. Most of the Gaiferous period was comparable in climate to modern-day Earth, and with Samsara III's stronger axial tilt than Earth, and therefore stronger seasons, the polar regions fluctuated dramatically between being temperate and bone-chillingly frigid. This understanding, as well as most ammoderms, which include lithoderms being fully capable of underwater breathing, led to the hypothesis that Paleontology hibernated during the long, cold winters, only reawakening once the surface of the ponds and lakes they inhabited unfroze, where they would then spend the short summer months eating and mating. Samsarian paleontologists speculate that eggs were laid unconsciously during hibernation and would hatch upon unfreezing. The oldest individual we have record of using these assumptions that one layer was added to the carapace each year, as is the case with most extant arthroderms, was an estimated 40 Samsarian years old at the time of death. A very long time for arthroderms. The Europods, when compared to their more basal hypsopod ancestors, can be considered strange in a multitude of ways. First and foremost, they're big. This is a trend, actually. Samsarian fauna, when contrasted with Earth fauna of comparable niches, are noticeably typically larger than the residents of almighty Terra, especially when geologic time is taken into consideration. In fact, this concept has even been attributed to an as of yet unofficial biological rule, Samsarian gigantism, coined by Dr. January Morris, a researcher studying the ecology of the bridge jungle. They sent their theory off to the OHA biology department and have yet to receive a response. In their own words, Samsarian gigantism is the series of phenomena where organisms of Samsara III often have significantly more mass than organisms of Earth with comparable ecological niches. Though the true reason is naturally unknown and likely unknowable, several theories have been raised. Most of them have to do with the geological characteristics of Samsara III itself. It has harsher temperatures than Earth, has higher gravity than Earth, has a denser atmosphere than Earth. It has a fast and somewhat eccentric orbit. It has stronger seasons, etc. The general consensus is that Samsara III is a pretty shitty place to live, so overall durability increases fitness. What was I talking about before this? Oh, right, Europods. The proliferation of shallow waterways across Samsara III as a result of the thermal maximum has led to a certain group of particularly adventurous Europods to explore a previously uncolonized habitat, freshwater. Similar to some theories about certain ostracoderm fish and Europod sea scorpions of Earth's Silurian and Devonian, it is believed that they moved into freshwater environments following a certain hugely instrumental ecological achievement, which will be covered at the end of the video. These Europods are almost universally of the clade Tanypoda, which, while not exclusively freshwater, do make up a bulk of the freshwater inhabitants that we have evidence of from this time period. Though only known from imprints found in rock deposits like the Caledon Shale, so named as it is farther north than human settlements have dared venture on Samsara III, which was compared to how the Romans called the lands north of Hadrian's Wall, one of Rome's border walls in Britannia, Caledonia. The tanypods of the Caledon Shale are remarkably well preserved despite their size. They as a clade are named for proportionally long legs compared to their ancestors, which are thought to have been beneficial in wading through rivers and lakes inundated with sand and gravel. Another strange adaptation of these animals are stalk eyes, which are believed to have been independently opposable, at least to some degree. A widened field of vision would have been useful in such an environment, as the presumed murky waters could effectively hide both predator and prey. Speaking of prey, we do not have a clear understanding of what they ate. Ancestral Europods have rough, rasping tooth plates in their throats, which are carried on into these descendants. These plates also seem to have moved into a drooping, tubular mouth sticking out of the front side of the organism, which ends up giving the average tanipod a visage not dissimilar to Max Rebo from those ancient Star Wars films. One thing you may have noticed from looking at this picture is arms, or at least something visually analogous. I'm going to be completely frank, we have no clue why. They are obviously adapted legs. Some assume they were for combat, some assume for mating, as the ancestral dodecapod reproductive area is in the front of the first pair of limbs. Others assume they were used to uproot plants like pteridophytes. I personally believe it was some combination of the three, with specifics varying based on species. I like these things, honestly. They're weird, and I like weird. Fish is a paraphyletic term. There is no definition for what us Earthlings would call fish that, 1, include all of what we would call fish, and 2, excludes what we would not call fish. For example, this is an Australian lungfish, and this is a Gnalgasters. They look awfully similar, don't they? You would classify both as fish, correct? Well, the Australian lungfish is a sarcopterygian, a lobed-finned fish, whereas the Gnalgasters is an actinopterygian, a ray-finned fish. You know what else is included in Sarcopterygii? Tetrapods. That means us. If these two are fish, but we are not fish, then that must mean that fish is not a taxonomic classification. Where am I going with this? Well, meet the Carnifidonts. They are, in essence, fish. Are they not? They have a fish-esque body plan, at least. If you have spent any amount of time in or around the coastal waters of Samsara III, as I have, you should be well acquainted with these bloodthirsty bastards. Genetic studies regarding their heritage have come back inconclusive. Do they descend from the same line as the Arthroderms, which many people think due to the banding of their exoskeleton, or are they more closely related to more typical paleontology, which can be seen in their vaguely Piscean form? We aren't sure, but what we do know, and what too many marine biologists have figured out the hard way, is their behavior and hunting strategy. They lack any sort of jaw, you see, and have throughout their entire history, even going as far back as 500 million years to the birth of their clade. They are somewhat like Earth sharks in that way. They have been quintessential carnifodonts for as long as there have been carnifodonts. They tend to be slender and somewhat serpentine, with the first pair of fins being dramatically larger than the other 5. Though perhaps their most defining feature is the skull plate, where they get their taxonomic name. Not unlike the previously mentioned Ostracoderms of Earth's past, carnifodonts have a thick and imposing exoskeletal shield adorning their heads. Typically made of calcium carbonate, the skull is an effective instrument of survival. There are sharp and serrated protrusions jutting out of the bottom, which carnifodonts use to open wounds on their prey, as they lack more precise hunting appendages. It is often quite difficult to take down prey of any meaningful size for them. As such, this group has resorted to taking down prey via means of blood loss and exhaustion, at which point they can use their actual mouth parts to tear off small chunks of often still living flesh. They are called butchers for a reason. Hell, the common name for many living species are some variations on butcher fish or butcher shark. Thankfully, due to the constraints of their feeding method, all extant species reach no more than 3 meters of head to tail. On average, of course. I once overheard a guy on the street talking about how he managed to find a rotting beached carcass of a butcher shark that was 5 meters long. I don't entirely believe him, but hey, it could be true. The flagellants have not received much attention in this lesson, and for good reason. I wanted to save the best for last. The Archethermic, up until this point, has very much been the time of the dodecapods. Flagellants were hit much harder by the unprotogene extinction than dodecapods, and they had trouble bouncing back initially. The only fast radiations of dodecapods post-calamity were the Onentorochids and Anthanaths, and they both had their problems. First of all, the Onentorochids were in competition with the Pelterpotonids and later Magnerpotonids, which led to them not ever reaching significant sizes nor diversity. The Anthanaths, on the other hand, were horribly inefficient filter feeders. Their bristles were not particularly plentiful nor dense, which means they could only catch so much plankton at any given time. There was a lot of plankton, yes, so they managed, but any level of competition would seriously hurt them. And it did. A basal branching of cotypods would develop an adaptation yet unseen on Samsara III. Teeth. The Odontophorans, as they are aptly called, threw a serious wrench into the ecological machine. Teeth are good at eating things, you see. The evolution of teeth on Earth is not fully understood. There are 2 main hypotheses: that they started out as scales that moved inwards, or that they were bone outcrops in the throat that moved outwards. Neither option was possible for the Odontophorans, so paleontologists have come up with several other ideas. For example, an early idea was that they started out as sharp protrusions of the jawbone that eventually lengthened. That is now considered wrong, as flagellants did not have bones at this point in time. Another idea is that they were actually made out of eyes. Before the Fimbulvateric period, all dodecapods had simple eyes covered in a hard filament, which is believed to have had a similar chemical composition to the teeth of modern Odontophorans. The so-called Eldritch theory postulates that mutations in the genes that regulate eye development led to eyes forming on the oral tendrils, though unconnected from the nervous system and therefore blind. Over time, these ocular teeth increased in size, sharpness, and number to better fit their newfound function. It is not a universally accepted theory, but it is more popular than most of the alternatives, with more evidence supporting it. If you have a theory, I'd love to hear it in the comments below. Nonetheless, no matter how it happened, the evolution of teeth among the Odontophorans gave them a very distinct advantage over the competition. This can be seen in their distribution. The oldest Odontophoran specimen we have is 492 million years old. half a meter long, and only found in one distinct geologic formation. However, by 487 million years ago, they were up to 2.5 meters long and spanned the whole globe. In 5 million years, Odontophorans at the very least quintupled in size and colonized the entire ocean. That is an impressive combination of feats, in my opinion. World conquest has been in the Odontophoran bloodline since the very beginning. These basal genera are believed to have been predators, and likely some of the most successful in their respective ecosystems, due to their as of yet unmatched appendages. Early Odontopherans were in a nearly competition-free environment, and if I have learned anything from Chinese history, it's that if good things are happening, eventually something bad will come along, oftentimes from within. What I'm saying is that they became bigger predators that were capable of predating on smaller predators. As they evolved, this branching of Odontophora, in essence, turned into sharks. Muscular, streamlined hypercarnivores with curved and often serrated teeth, apex predators at the top of the food chain that frequently feed on organisms larger than themselves. My students, if you are ever so unfortunate to find yourself in any of the many oceans or seas of Samsara III, you should listen well to what I have to say, as it might save your life. Yes, the clade to which I refer are the infamous alien emissaries of Davy Jones himself, the group of Samsarian animals which as of yet has caused more loss of human life on the planet than any other source, a family of bona fide living fossils having lived for only a wee bit under 500 million years. The Gnalgasters, scientifically known by the name Gonzodonta. The average gonzodont reaches a solid 6 meters from mouth to tail, and these ancient varieties were not much smaller, being around 4.5 meters long. Today, that would not be particularly large, but the gonzodonts were at that point the largest predators Samsara III had ever seen, and the most well-equipped. They are capable of taking on nearly anything that did not have a form of armor. As without jawbones, they did not have the necessary bite force to puncture, say, a lithoderm. However, basically, everything else was on the menu. Uropods, tanopods, anenterochids, early odontopherans, and even the amphionaths. The undisputed largest animals on the planet at this point. It is unknown just how diverse they were at this point in time, as what little remains we do have look pretty much identical to one another. To be fair, the only hard tissue we have to go off of are teeth and eyes. This illustration here is based on comparative anatomy using extant and more recently extinct gonzodonts as a base, and taking away things that we assume were later derivations. We're left with this. There is not much to say about these early genera, such as the one shown here, Gnalgaster, but I'm sure we'll come back to them at some point in the future. Now, as I promised, a couple of tips on how to actually deal with an encounter with a living one. First of all, they do not seem to dislike the taste of man flesh, so don't count on you tasting bad to ward one off. With sharks, the common tip is to punch them as hard as you can on the tip of the snout, and that'll discombobulate it. But Gnalgasters don't have snouts, so that obviously is not applicable. The most common tip I've heard from people who have encountered them is that if one does come close in a threatening manner, to either shove your entire arm down its throat, which seems a bit dangerous, or to hook your hand into their gills and yank, which are on the bottom of the body, right in front of the first pair of fins. Seems less dangerous, but also not necessarily as effective. To be fair, all these people had scarring all over their bodies, so maybe take their advice with a grain of salt. My piece of advice would be to just not get in the water, but if that is absolutely necessary, bring a cattle prod. Electricity works on most organisms, no matter the planet. Unless it's a really big one, then you're just screwed. We are nearly done, but I thought I'd end this segment off with a revolutionary innovation in terms of life on Samsara III. Plants have naturally diversified since the beginning of life on Samsara III, but they have always been fully confined to the water. Not anymore. The first organisms to reach out of the water began to pop up during the Archethermic, starting in tide pools and shallow rivers. One of the hardest hurdles to overcome when it comes to terrestrialization is preventing desiccation, making sure the body maintains enough water. The trypophytes, as they're called, came up with an, in my opinion, genius method for water retention. They turned into bowls. Like the kappa of Japanese folklore, these plants require their hollow stems to be filled with water in order to stay moist until the next high tide. This is not that strenuous on the plant, however, as Samsarian tides are frequent and large. They would have had to go at most 3 to 4 hours without refilling their water. It may not seem like a big leap, but I promise you it goes somewhere. It is important that I touch on this. Speaking of which, I'm done touching on this. That brings this lesson to a close. If you have any further questions you would like answered, ask them in the comments or in the Discord server, which will be linked in the description, and I'll try to get back to you as soon as possible. I get that this episode took a while, I will admit. I have very little drive to do anything anymore, but I thought I might as well get one last video out before I go to Germany for a month. So here I am. I'll try my darndest to get another episode out before I go back to school in a few months. Maybe I'll get one out once a month for the summer. I don't know. Thank you for watching. I do wholeheartedly appreciate the support. Believe it or not, I do enjoy making these. Subscribe if you want to. There's really no reason not to if you made it to the end of the video. But it's still ultimately your choice. Welp, you have a good day now. I'll be seeing you. Bye.